You've seen some examples of calculations of the moment generating function of random variables with some of the well-known distributions. The normal is the big one, so let's crank this out. We are going to start with a standard normal as always, and we're going to find its moment generating function. And so the moment generating function at any t is by definition the expectation of e to the t times the random variable. That is the calculation that we have to do is that of the expectation of some generic non-linear function. And so we take the generic little z, we apply the function to it, we multiply by the density of z, and then we integrate. So if I sort that out, notice that I'm not pulling out the 1 over root 2 pi. What I'm going to attempt to do is I'm going to attempt to do the calculus without doing the calculus. I'm going to attempt to do it with probability theory. Let's see if I can do that. So I have e to the minus half z squared minus twice t z dz, and I look at z squared minus twice tz, and that's almost a square. I am off by a t squared. If I had a plus t squared, that would be a square, and that would be quite nice. So why don't we put that in and see what happens? Okay, well, I've stuck in something that completes the square in that quadratic, but you can't just put in factors, you have to take them out as well. And I believe what I have introduced is a factor of e to the minus half t squared, so I better multiply by e to the plus half t squared. And then I'm fine. I'm integrating with respect to z. T is a constant, so I can mess around with it as I wish. And now we are going to look at what we've got in that integral. It looks like I've made my life harder, but I've actually made it easier. So I have integral from minus infinity to infinity, 1 over root 2 pi e to the minus half z minus t all squared dz. And this is a density. Which density is it? It is a normal density. Which normal? We can spot the mean. So the variable is z. T is the constant. There's your mean. And the SD, in the normal density, you see a 1 over root 2 pi sigma, and then a variable minus mean over sigma, and you're not seeing it, because it's 1. Whatever it is, it's a density. And if you integrate a density over the entire line, what do you get? You get 1. And so I still have my e to the t squared over 2 times 1, which is e to the t squared over 2. And so this is a finite number, and so it doesn't matter what t is, I'm going to get a finite number. And so what I have here is that if z is standard normal, then the moment generating function is e to the t squared divided by 2. For all t. Very well-behaved distribution. If x is normal but not standard normal, then x is a linear transformation of z. Where z is x in standard units, so z is standard normal. And so now by linear transformation facts, the moment generating function of x at t is gotten by, so you got to look up your linear transformation rules, e to the minus mu t, the moment generating function of z at the point sigma t. And so that is e to the mu t, and then e to the sigma t all squared over 2, and this is usually written as e to the mu t plus sigma squared t squared divided by 2, and t can be any number. And that is your normal moment generating function, which is e to the power quadratic in t. And what do we notice about this quadratic? We notice that the coefficient of t squared is positive. Because it's sigma squared over 2, and sigma squared is variance. And we notice that there is no constant in the quadratic. And why is there no constant in the quadratic? Supposing I had e to the 5 plus mu t plus sigma squared t squared over 2. What would the value of that function be at t equals 0? Well, the mu t would go away, the sigma squared t squared over 2 would go away, and I would be left with the 5, and the value of my function would be e to the power 5, which is not 1. So that would not be a moment generating function. Now, what you've seen is that moment generating functions identify the distribution. So if you see any moment generating function, if this is given to you as a moment generating function, then what's the distribution? It's normal. You can see the mean, it's minus 2. And what is the variance? Well, the coefficient of t squared in your MGF is sigma squared over 2. So 3 is equal to sigma squared over 2, and therefore sigma squared is equal to 6.